Welcome back to the lecture on pair formation processes in the context of sexually transmitted diseases. So just a reminder, we have just looked into formulation of a model that captures pair formation process, and now are ready to add to this the dynamics of the disease, the whole point of this exercise. So in order to do that, we will set forth the following assumptions, that we are considering a population where sexually transmitted disease circulates. Now, the progression of this disease could be described with a so-called susceptible infected susceptible framework infection, i.e. the individuals get infected, recover, and become susceptible again. No immunity is conferred. For example, a disease that comes to mind is chlamydia. We consider a population of men and women who are represented equally in the population. We assume that individuals can be either single or in a relationship. And we assume that individuals are serially monogamous, so we could use the framework that we've just developed. The disease that we consider does not induce mortality, much like it doesn't induce immunity. Overall, we assume that at the start of the disease invasion, we start in a disease-free, such that the pair formation process is in the equilibrium itself. Population is at a constant size, and the proportion of individuals in pairs or being single is constant as well, or as near constant as could possibly be. Now let's look into what will go into this model. So first and foremost, not only do we now delineate the population by their relationship status, we also delineate the pairs by the infection statuses of their participant. Similar thing goes for the for the single individuals. And so now instead of 2 compartments, we have 5. As far as the single individuals go, we have these who are susceptible and these who are infected and infectious. As far as the pair goes, we are assuming that the following combinations of partners can appear. Either 2 susceptibles are in a pair, or we have one individual who is susceptible and the other one who is infected, or we have a pairing of 2 infected individuals. Now, of course, the individuals circulate between these compartments through the process we have just discussed, through the pair formation and dissolution process. So in order to create a pair where 2 individuals are susceptible, we would need 2 single individuals. Should this pair dissolve, these individuals will go back, both of them to the single susceptible state. Similarly, if we have 2 infected individuals that create a pair that will go into compartment PII, this pair can also dissolve, in which case both individuals will go back to the single infected stage. And finally, susceptible and infected individuals can team up to create a mixed couple where one person is infected and the other person is susceptible. Should this couple break up, the susceptible partner will go to the state of being single and susceptible, while their infected partner will go into the state of a single and infected. Note that overall, the only place where the transmission of the disease can take place is this compartment here, PSI, where infected individual has infectious contacts with the susceptible individuals. If, for example, in PSS, nobody to infect the other person. In PII, both partners are already infected. And so the only infectious event that can take place will take place in the compartment PSI. Now, recovery is other animal. It affects a number of compartments, not just one. We know that individuals can recover while being single and infectious due to, for example, either experiencing unpleasant symptoms or just thinking back and perhaps thinking that, hey, I might be infected, I might go to get tested, or even recover spontaneously. Similarly, for example, if we're dealing with PII pair, one of the partners might recover, in which case the status of the pair will change from PII to PSI. And of course, the only remaining partner in a PSI pair that is infected can also recover, in which case now both of the partners will become susceptible, and the pair will change their status from PSI to PSS. So with this description of the process, we are now equipped to formulate a system of ordinary differential equations that will describe these dynamics. So we will start with a pair formation process. Much like before, we are assuming that single individuals get recruited in the pair formation process irregardless of their infection status at a rate that is proportional to the size of the respective compartments. So overall, individuals leave compartment XS to form a pair with rate rho XS, and they leave XI compartment for the same purpose with the rate rho XY. And of course, once they do that, they can end up in any one of these two compartments. So let's think for a second, what is it that we're seeing in front of us? So let's consider a pair PSS. So say this is a pair where two susceptible individuals form a pair. So individuals arrive at this compartment with rate rho XS. And now, if I am a susceptible individual, what is the probability of me encountering a second single susceptible individual? Well, it's given by the fraction XS divided by the total number of the single individuals, which is given by XS plus XY. Now, if I will do this calculation for each type of a single individual, I will be counting double. And in order to actually get rid of this counting double, we need to introduce fraction 1/2 in front of this ratio. Similar type of train of thought will go into the incoming rate of the relationship formations for PII compartments. So individuals who are infected get recruited to form a new pair with rho XI, and now for each infected individual who enters a pair formation process, what is the probability that their partner is actually infected? Well, it's given by the prevalence of infected single individuals over the total amount of the single individuals in the population. And of course, since we will do this calculation per each infected individual in the population, we will be counting double, and in order to get rid of that, we will need to introduce the fraction of 1/2 here. Slightly different story when we're considering a mixed pair, where one individual is susceptible and the other individual is infected. So let's say we start with a susceptible individual, although the same chain of thought can apply to the infected individual without loss to generality. So we know that susceptible individuals get recruited into a pair with rate rho XS. Now the probability that their partner is infected is of course given by XI divided by the total number of XS plus XI. However, at this stage we do not count double, we count the only possible option for each single individual, but we do not count double, and therefore there is no need to actually insert 1/2 here. Now pairs can form, pairs can dissolve. So enter the dissolution rates of the partnerships. Let's start with couples that are of the same infectious status, so PSS and PII. Now, when a pair where both partners are susceptible dissolves, two single susceptible individuals appear, as represented by this number 2 here. Similarly, when a couple where both partners are infected dissolves, both of them will go to the single compartment where individuals are infected, and since it's both of them, we obtain the number 2 here. Now finally, when a couple where one partner is infected and the other partner is susceptible dissolves, the susceptible partner will go into XS compartment while infected partner will go into XY compartment. That's why you do not see a 2 here. So this is a pair formation process. Now let's overlay this with infection and recovery processes. Let's start simple. Let's start with the recovery of the single individuals. This can move only in one direction. Infected individual recovers, single individual recovers, and as such they become susceptible single individual. Another place where recovery can take place is when the partner who is infected in the mixed couple recovers. The moment they recover, the couple changes their status and now becomes PSS. So we lose one couple here, gain one couple here, and we do so with the rate of gamma PSI. Quite could go the other way around. The infected person in this mixed couple, instead of recovering, can actually get their partner infected as well. And so now both of the partners recover. And we will lose this couple from the compartment PSI, and we will gain this couple in the compartment PII. This happens with the rate that is proportional to the number of mixed couples. And constant beta, which itself is a product of the frequency of infectious contacts and efficiency, probability of transmitting per single contact. Finally, one last infectious event that can happen is actually a couple. When we look at the couple where both individuals are infected, one of the partners can recover, and as the result, the couple will switch its status from PII to PSI. We assume that only one partner can do so at a time. However, since we don't know which one of the partners can do that, and this event of recovery of one of the partners is then twice as likely, we introduce this factor of 2. This model is already good enough to study the short-term dynamics of sexually transmitted diseases. It can be further extended by introducing demographic process parameters, for example, birth and death, or we can say that every single individual is being born into population at a constant rate, and they're being born as a single individual who is healthy. Individuals can die at any stage of their being either as a single or as a person in a couple, either they're being infected or they're being susceptible. Now we, as announced before, we're assuming that both pair formation processes and birth and death processes are not affected by the disease. So individuals die pretty much at the same rate regardless of their relationship status or infection status. Now, what we have right now is no longer very small. We have a system of 5 equations. They're a little bit harder to deal with. And that's sort of is not the point of deterministic model, which is one of hallmarks of which is easiness and compactness which we can work with. However, lucky for us, if we impose a number of assumptions, we can reduce the dimensions of the system from 5 to 3. If we assume that the model, the system, resides in the pair formation equilibrium and in the population demographic equilibrium, then the number of pairs, the number of single individuals, and the total population size is constant. And by making the following substitutions, for example, XS equals to X star minus XI and PSS equals to P star minus PSI and PII, where X star and P star are the number of single individuals and the number of pairs at the pair formation equilibrium, then we can move from the system of 5 equations to the system of 3 equations, like so. You will notice that the elimination that we performed pretty much removed all the variables that have nothing to do with the being infected. So what we are left with here as a 3-dimensional system is whole compartments where some sort of infectious dynamic can take place. Either we're looking at single infected individuals, or we're looking at a couple where at least one of the partners is infected, or we're looking at the system, at the equation where both partners are infected. And therefore, we can keep track of our prevalence of the disease in the population by keeping track of the following variable xi plus psi plus 2 pii. This concludes this part of the lecture where we develop a pair formation model coupled with the disease dynamic model. And in the subsequent knowledge video, we will look on things that we can learn from analyzing such a system.